We are going to talk about limits of trig functions. Now, if you wanted, or limits involving trig functions, if you're going to take the limit of just a trig function, trig of x, that means sine of x or cosine of x or tangent of x or cosecant of x, etc. It is nothing more than direct substitution. It equals to the trig of c. Where trig of c, if this said sine of x, then the limit would be the sine of c. For example, the limit is x goes to c of the secant of x. This will equal to the secant of c. It's just direct substitution. It is just direct substitution. So if you were asked what is the limit as x goes to 0 of just a simple cosine function, this would be cosine of 0, which is 1, and we're done. But sometimes you don't have just the limit of a trig function. You may have the limit of a trig function squared. You may have the limit of x squared times the trig function. You might have the limit of a trig function divided by a trig function. That's not just the limit of a trig function. If it gets more complicated, it's a little bit harder. For example, what is the limit as x goes to 0 of sine x over cosine x? Over x. Well, direct substitution gives you the sine of 0, which is 0, over x, which is 0. That means it's indeterminate. We can't figure out yet what it equals. Well, Lupertal would come along and he would say take the derivative of the top, take the derivative of the bottom, and then evaluate the limit. Well, this is cosine of 0 over 1. The rule for dividing by 1 is don't bother. So I get 1. That is, this limit was 1, or is 1. Now, let us try to understand this limit a little bit better. We have the limit as x goes to 0 of the sine of x over x. Notice that what we're taking the sine up, that is the angle, and the denominator are both the same. That's the first, say this answer is 1. That's the first thing that has to be true. Whatever you're taking the sine of, that's what you're dividing by. The second thing is, when x goes to that number, these have to go to 0. And of course, if that goes to 0, then x goes to 0. So it passed both criteria to be 1. If you have the limit as x approaches 2 of sine of x minus 2 divided by x minus 2. Well, I have the sine of this angle divided by this. What's in green are equal. Past condition 1 for this to equal 1. Condition 2 says when x approaches 2, this is supposed to be 0. And of course, 2 minus 2 is 0. It passed the second test. The limit is 1. If you have the limit as x goes to 3 of the sine of x squared minus 9 all over x squared minus 9, this is a good candidate to ask if it equals 1. Because I'm taking the sine of this and I'm dividing by the same thing as what I was taking the angle of, the sine of. So it passed the first condition. the next condition is the limit as x goes to 3, it should make those 0. And of course, you near 3, you square it, you'll get near 9. Take away 9, 0. This is 1. Here's a good one. What is the limit as x goes to infinity of the sine of 1 over x over 1 over x? Well, it clearly passed the first test. The sine of this, and we're dividing by that same angle. The second thing is, when x approaches infinity, 1 over x is approaching 0. That's enough for me. This equals 1. Okay. Now, I do want to point out one thing though. This limit that I gave you, it was somewhat spoon-fed to you. Generally, instead of dividing by 1 over x, we can multiply by its reciprocal, which is x. You'd see the problem like that. You, being the student, have to realize, you know what? When x goes to infinity, that goes to 0. So you know what? Instead of multiplying by x, I'm going to divide by the reciprocal. Okay? Now, the angle and the denominator are the same. The sine of this angle is what I'm dividing by. Oh yeah, we just said that goes to 0 and that's going to go to 0, so yeah, it's 1. Now, you need to sometimes think a little bit. If this fraction goes to 0, that means that for small x, the sine of x is very close to x. How else is that fraction going to be 1? A fraction is 1 when the top and the bottom are equal. A limit of a quotient is 1 if the numerator is close to the denominator. Okay? So when x is small, the sine of x is approximately x. So what would the limit as x goes to 0 of x over sine x be? Well, when x is really, really small, x and sine x are about the same. So we get 1. You can prove it more rigorously, the limit as x goes to 0 of sine x over x. Well, this is equal to the limit as x goes to 0 of sine x over x to the first. But this is the limit as x goes to 0 of... Oh, excuse me. I'm not taking the right limit. We want to figure out a formula for this limit. Well, that function is equals to itself to the first power. But now, if I do x over sine x to the -1 raised to the -1, remember, you're supposed to multiply those two exponents. And -1 times -1 is 1. And the fraction inside, x over sine x to the half, well, that's sine x over x to the -1. But we have this theorem that says that you can take the limit in this case of diffraction, and then after you find that limit, then raise it to the -1. Ooh, I know that limit, it's 1. And when you take the reciprocal of 1, you get 1. That is, this fraction, that limit, really is 1. But it's kind of intuitively clear that that should be true, because the reason is for small x, sine x and x are about the same. How else would their limit of the fraction be 0, of their quotient be 0? So if somebody asks you, what is this approximately, how much is the sine of 0.000314? Well, you should respond back with, it's approximately that. Okay, why else would this over that, notice it's near 0, why would the division of those two be near 1 if they weren't about equal? Okay. Now, let us play some more games with this function. I like this function. Suppose you have the limit as x goes to 0 of the sine of 5x over x. Well, if you had a 5 there, you would know what the limit is. So put the 5 there and then multiply by 5. In fact, that 5 in the numerator can come in front of the fraction, or the limit I meant to say. The sine of 5x over 5x, these are both the same, and when x gets closer to 0, those get closer to 0 as well. So that limit is 1, but we want 5 times the limit. Now let us look at the original problem. You have sine 5x over x, and the answer was 5. Might that be a pattern? Suppose you have the limit as x goes to 0 of the sine of a times x divided by b times x. The first thing I would do is get that b out of there. This is the limit as x goes to 0. I can factor the b out in front, but I won't. Times the sine of ax over x. Now, I can multiply the bottom by a, and that's perfect for this. But then I better multiply the top by a. Make this legit. We have the limit as x goes to 0 of a times 1, which is a, over b, times the sine of ax over ax. I guess we should say a is not 0. Okay, the limit is x goes to 0. So this becomes the limit of this, which is just a over b, times the limit of that fraction, which is 1. So we get a over b. You mean the answer is this? Yes. Yes. See, if I put 5 in there and 7 in there, maybe it was a coincidence that I got 5 over 7. But that's why I did it in general. So now I know. Somebody asked me, what is the limit as x goes to 0 of sine of 17x over pi x? I know the answer is 17 over pi. That's the answer. This theorem told me that. Okay, you always get a over b. So, just one more of these. So, suppose you were given the limit as x goes to 0 of bx over sine of ax. Well, we know if the b and the a weren't there, we would just get 1. Well, we can move the b, but we can't get rid of the a. That is, that doesn't equal, sine of ax, for example, doesn't equal to a times sine x. So what we want to do is, well, we need to keep the sine ax, and instead of x on the top, we have to have a times x on the top. We have to have a times x. So there's the b, and there's the a. So there's the b that we're supposed to have, and everything in blue I put in out of nowhere. Well, this is the limit of that fraction, which is b over a, times the limit of this fraction. Both of those are the same. There's my necessary sign, and as x goes to 0, these go to 0. That means it's 1. We get b over a. You mean once again we can read off the answer? Apparently so. Apparently so. Suppose you have this limit. The limit as x approaches 0 of 1 minus cosine x over x. Well, if you directly substitute, you get 1 minus cosine of 0 is 1. So you get 0 over 0. Now, one way of doing this problem is to somehow, you have that x, somehow get a sine x on top of it. You have to get a sine x on top of it. So what you do is you multiply. So you want to change the way the top looks. Anytime you want to change the way something looks like, you multiply by 1. And this is how I'm going to choose my 1. So the bottom, so still the limit as x approaches 0. The denominator is just x times 1 plus cosine x. But the numerator, it's in the form of a minus b times a plus b. So we get back a squared minus b squared. That's a, and when I square it, I get 1 minus, that's b, and when I square it, get back cosine square x. Now, we know that sine squared x plus cosine squared x is 1. If I take this away from the left side, I only have sine squared x left. But I better take it away from the right side to make it equal. So we know that, that's sine squared x. So this is the limit as x goes to 0 of sine squared x. But above that x right there, I'm going to put sine x. And then I have another sine x, and that gets divided by 1 plus cosine x. I'm going to save that because I know that limit. This is just great. So we have the limit of the first fraction, which is 1, times the limit of the second fraction. Well, if you direct substitute, the sine of 0 is 0 over 1 plus the cosine of 0 is 1. So you have 1 times 0 over 2, which is 1 times 0, which is 0. That's one way of doing this problem. One may say, that was unnecessarily hard. Why don't we just, since we got 0 over 0, why don't we just invoke Lupertal's rule? The derivative of 1 is 0. The derivative of negative cosine x is sine x. Negative sine x. Positive sine x, excuse me. And the derivative of the derivative of x is 1. So this is just sine x, and when you have a trig function, the limit of the trig function is substitution, and sine is 0, just what I got before. What if you have this problem? The limit as x approaches 0 of cosine x times tangent x all over x. If you direct substitute, cosine of 0 is 1, tangent of 0 is 0. You multiply them, you get 0 over 0. Now, you can use Lupertal's rule, but that's going to involve taking a derivative of the top, which will involve us using the product rule. Lupertal's rule says you take the derivative of the top and you divide that by the derivative of the bottom. It never said that, oh, when you take the derivative of a product, from now on, don't use the product rule. It didn't say that. It says take the derivative of the top, and if it's a product, you use the product rule. If it's a quotient, you use the quotient rule. You use the rules that you know to take the derivative of such a function. Okay. But again, I don't think that's the way to go here. Like I said, I would love, whenever I have a trig function that's indeterminate and part of it just has x, one factor is x, I'd do anything to get a sine x either above or below it. Well, cosine x is cosine x, tangent x is sine x over cosine x. Coincidentally, those cancel out, and I get my sine x over x. That's 1. This limit is 1. It's just disguised as sine x over x. What if you have the limit as x goes to 0 of the secant of x over x? Well, if you directly substitute, you get secant of 0 over 0. Secant is the reciprocal of the cosine. Well, the cosine of 0 is 1, and the reciprocal of that is 1. You get this, and this is undefined. I mean, you could have said that this is the limit as x goes to 0. I'll keep the x on the bottom, and this on top, well, that's the same as cosine x in the bottom with the 1 on top. Once again, you get 1 over 1 times 0. Cosine of 0 is 1. X is 0. You get 1 over 0, which is undefined. You don't use Lupertal's rule, because Lupertal's rule is only when you have 0 over 0, and you have 1 over 0, or you have infinity over infinity, where we don't care if the infinities are plus or minus. That finishes this section on limits of trig functions.